Good morning everyone. Today we will see LAUE equations. You can use any solid state physics textbook for this particular topic, but for the illustrations that I am using in this presentation, I have used solid state physics by M.A. Wahab. Important topics that we are going to see today is Bragg condition, LAUE equations, and the equivalence of these two. Basically, both Bragg equations and LAUE equations, they give us the condition for diffraction when a suitable electromagnetic wave is passing through a crystal. However, there are some basic differences in the approach of these two equations. So the way in which these two equations are derived, it has got some fundamental differences which we are going to see right now. So we will quickly review the Bragg condition, which is given by n lambda is equal to 2d sine theta. So how Bragg derived this equation, we'll just review it. You can look at the different planes which are indicated by their Miller indices at scale. Separation between adjacent planes is given by d, which is the interplanar spacing. So the planes are all these planes are parallel planes. They indicate a set of planes having the same Miller indices at scale. So when you think about an X-ray beam which is falling on the crystal, let us look at the wave which is getting diffracted from the first two planes. The top plane and the plane which is beneath this. If you assume that the direction of the incident X-ray is given by this, and if the direction of the diffracted beam is given by this direction, after diffraction the waves are going along this direction. So both these two planes are contributing to the diffracted waves in this direction. Just for the derivation, actually X-ray beams will be penetrating deep into the, it can penetrate deep into the crystal, but even for the normal configuration of the X-ray XRD experiment that we do, this angle theta is chosen in such a way that it will be penetrating to a small depth, but in that case also it will be capable of going into the depth of the material in such a way that the diffraction can take place from thousands of consecutive planes. But for this derivation we are thinking about the first two planes. So what is the condition for getting constructive interference here? It means the path difference between these two waves which are diffracted from the first and second planes, it should be equal to an integral multiple of lambda, where lambda is the wavelength of the X-ray beam which is used. So you can easily see that looking at the this diagram, you can see that this is the path difference. BC plus CD is the path difference, and BC and CD you can express it in terms of theta, and it is equal to d sine theta. So the total path difference between these two waves which are getting diffracted from the first two planes will be equal to 2d sine theta, and for constructive interference that should be equal to n lambda. So that means for a given grazing angle theta, you will be able to the diffraction or Bragg condition will be satisfied when n lambda is equal to 2d sine theta, which means along this direction, when you actually do the XRD experiment along this direction, we will be able to see a bright beam coming, or if you keep a detector over here it will record high intensity, or if you take a photograph you will be able to get a bright spot in this direction. So this is the Bragg condition. Now when you look at the Bragg condition, you will see that it is actually the consequence of the periodicity of the crystal planes. Whereas in each of these crystal planes there are atoms which are arranged in a specific manner, but in the Bragg derivation, the way in which these atoms are arranged in each of these planes, it is not taken into account. So in that context we will see LAUE equations. LAUE equations, we can say that it is more general compared to Bragg condition. Both will be giving you the condition for diffraction, or a condition for diffraction in such a way that the condition for getting bright spots in diffraction. So whereas when Bragg equation is taking into account the periodicity of the lattice planes to derive this equation, LAUE equations are derived by taking into account the periodicity of the lattice points, or in each of these planes how the atoms are arranged. That is taken into account to derive the LAUE equations. So that is why we say LAUE equations are more general than Bragg equation. So when you look at the LAUE equations, these can be, I have listed out 3 points. These can be taken to be the features of the LAUE conditions, or it is they will make up sort of arguments which we can use in order to derive LAUE equations, or the fundamental arguments that we are considering when we think about the derivation of LAUE equations. So the argument is that when X-rays are falling on a crystal, there will be, or when you think about the X-rays which are falling on a row of atoms, when the X-rays are falling into the crystal, each of these atoms will be capable of scattering these X-rays in all possible directions. But in certain directions they will undergo constructive interference, or they will get reinforced, and it will give rise to bright diffraction spots. So in order to get this constructive interference, we will have to think about a minimum of 2 waves. So in the Bragg equation, these 2 waves were coming from diffraction from 2 successive planes, whereas in the case of LAUE equations, these 2 waves are assumed to be coming from diffraction from 2 adjacent atoms. So this equation will help you understand that concept in a better way. You have got this dotted line which indicates a row of atoms. You have got this A and D, and the next point you can assume them to be the lattice constants, and at this lattice constant we have got the basis or the group of atoms. So here what we are going to assume is that, for simplicity, we'll just assume a row of atoms or a one-dimensional periodic structure. So what we have is, you have got an incident wave which is coming this way, and it is making an angle alpha 0 with the line of atoms, and it is after diffraction it is propagating along this direction. So what we have is, we have to think about what are the conditions under which here we will be able to get a bright spot. Okay, so here what we do is, we have to consider 2 beams, a minimum of 2 beams which can undergo interference. So those 2 beams will assume that one after diffraction from the atom which is at the position A, and the other one is from after diffraction from the atom which is positioned at D. So what we have to see is, if you look at the diagram, what we have to see is the path difference between these 2 rays which are scattered from atom A and D. By the time it reaches this spot or a detector that we are going to keep here, by the time it reaches the detector, they must be satisfying the condition for constructive interference, which means path difference should be equal to integral multiple of wavelength of the X-ray beam. Okay, so here just like in the previous example, we have expressed the path difference in terms of interplanar spacing. Here we will express the path difference in terms of A. A is the lattice constant. You can see it is a separation between adjacent atoms along this direction. Okay, so you can assume that this is the direction of one of the primitive lattice vectors. Okay, which means if you put a vector symbol above A, that will be one of the primitive lattice vectors. I'm saying one of the primitive lattice vectors in the context of 3-dimensional crystal, but right now we are thinking only about a 1-dimensional arrangement, because we will begin with the simple concept and then we will extend that to 2-dimension and then later to 3-dimension. So that is what we intend to do. So what we have is, we just have to look at how much will be the path difference over here. So for that we draw perpendicular A, B and CD, and if you look at the diagram you will be able to see the path difference is will be equal to AC minus BD, because this wave it is making it is traveling an extra path equal to BD, whereas this wave it is traveling an extra path equal to AC. So by the time these two waves reach here, the path difference will be equal to AC minus BD, and both these AC and BD we will be able to express in terms of alpha and alpha 0. Okay, so that is what we are going to do. You can see that see, for example, here AC is the adjacent side for alpha. So in terms of A, small a, you can write AC as small a cos alpha. Similarly, BD will be equal to small letter a cos alpha 0. Okay, so that is the, so AC minus BD we will write it as a path difference, and that should be equated to integral multiple of lambda in order to have constructive interference. And we assume that if alpha indicates the direction at which we are going to get the constructively interfered beam, it will result in a bright diffraction spot. And for a given value of given direction of incidence alpha 0, we can imagine a set of alpha set of rays having the same value alpha with respect to this line of atoms, and all those rays will be lying on the surface of a cone like this. So this cone actually indicates the condition under which bright diffraction condition, let us say, in terms of the LAUE equations, or as per LAUE treatment, this cone indicates the diffraction condition. Okay, for a given value of alpha 0, we have got a cone in such a way that all the waves which are lying on the surface of the cone will indicate the directions along which we will be able to get bright diffracted spots. So that is actually what is explained here. The total line in the previous diagram, it is the row of atoms. So you can just go through this and see, I have already explained. Now when you look at the path difference, as I told you earlier, it is AC minus BD, and I have copied a portion of that picture again here, and that path difference is equal to A cos alpha minus A cos alpha 0. So that is a path difference, and we equate it to integral multiple of lambda. E is an integer, it can take values 0, plus or minus 1, plus or minus 2, etc. Where when 0 means it is the 0th order diffraction. Okay, plus 1 and minus 1, plus 2 and minus 2, all these indicate higher order diffraction. So when you look at these equations, we will be able to see, for example, when you put E is equal to 0, that gives rise to 0th order diffraction, which means cos alpha equal to, cos alpha should be equal to cos alpha 0, or alpha equal to alpha 0, which means the wave will be passing undeviated. Okay, so that is what we refer as the 0th order diffraction. Then when you keep on increasing the value of E, you will be able to see, for example, if you compare the values of alpha for a given value of alpha 0 is the incident wave direction, we will fix it, and for that incident specific value of incident wave direction, there can be different orders of diffraction. So that means if you can just examine this equation and see, for example, when E is larger, alpha will be small. Alpha is the direction along which the scattered wave or the diffracted wave will be propagating, and it will in such a way that it will satisfy the condition for constructive interference and gives rise to bright spots. So when for higher orders of diffraction, you examine this equation and you will see that alpha will be less. So that means for a given value of incident wave, there will be different cones indicating different orders of diffraction, and these cones will be all concentric cones, as you can see in the next diagram. See, this is the cone that I was talking about for the particular value of alpha that we have been talking about. And for when you put the value different integers for E, they can be actually plus or minus. then E is equal to 0 is the zeroth order diffraction, or the wave will be passing undeviated. I have illustrated it in the next slide. See, so you can assume this to be the the wave when it is going. For example, this wave, this can be treated to be the zeroth order diffraction. The wave is, let us say, wave is coming this way and it is passing undeviated. So you have got different cones indicated by the numbers 1, 2, -1, -2, etc. They represent different orders of diffraction, and you can see that all these cones are surrounding the line of atoms, which is this one, and higher order, the cones indicating the higher order diffraction, it will be having a smaller value of a smaller diffraction angle compared to the lower order diffraction cones, or the cones indicating the higher order diffraction, they will all be lying within cones indicating lower order diffraction. So let us take it that way. So anyway, all these cones, they are for basically what we have seen is when we consider a line of atoms, or atoms which are placed periodically along one direction, we have got different cones indicating the diffraction condition, which means when this diffraction condition is satisfied, we will be able to get bright spots for a given incident wave direction. For each of these cones are representing possible different different orders of diffraction for a given incident wave direction. Now if you look at that that equation which I have told you right now, which is A cos alpha minus cos alpha 0 is equal to E lambda, we can write that equation in terms of vector notation. For example, I told you this A is the lattice constant. When you take the magnitude, it is the lattice constant, or it is the separation between adjacent atoms. But in the case of one-dimensional periodicity, if you if you just put a vector symbol over A, that will indicate the primitive translation vector, okay, or it indicates a translation vector in that one-dimensional arrangement of atoms. And we will assume S0 to be the direction of the incident X-ray beam and S to be the direction of the diffracted X-ray beam. They will be indicated by the corresponding direction cosines alpha 0 and alpha. So that means this equation we will be able to write, since we have got A cos alpha, we can write it as a dot product in terms of the corresponding vectors. So for example, A cos alpha is equal to A dot S, where S is the unit vector in the direction of the incident wave, in the direction of the diffracted wave. Alpha is the diffraction direction, and S0 is the unit vector in the direction of the incident wave. Corresponding direction cosine is cos alpha 0. So that means this equation A dot S minus S0 and A cos alpha minus cos alpha 0, these two equations are equivalent. So that's why we are writing it like this, and it is equal to, when it actually is the path difference, and when it is equal to integral multiple of lambda, we get the condition to obtain bright diffraction pattern. Now what we are going to see is we have to add one more plane. For example, along the B direction, we can think about a row of atoms which are arranged along the B direction. So for a given angle of given incident wave direction, which is given by alpha 0, for a given incident wave direction given by alpha 0, for a given incident wave direction given by S0, there will be different cones for diffraction from atoms which are placed along the A direction and also along B direction. So what we have is the equation which we have written down right now for a series of atoms or a line of atoms which are arranged along the A direction. an equation similar to that will be existing for representing the diffraction condition to be satisfied by the atoms which are placed along the B direction as well. So that means what we actually do is we assume that we have got a specific incident wave direction which is given by S0, because that is actually what we do and get in XRD experiment. We send the X-ray waves in a particular direction which is specified by the Bragg angle, or Bragg angle in the Bragg treatment, or in the LAUE treatment it is specified by S0. And if diffraction condition is satisfied, we will be getting a bright spot, and that bright spot, the direction in which we are going to get the bright spot, it is a specific direction, and that is given by this S. Okay, so that means whether it be atoms which are arranged along A direction or B direction, these two vectors, S0 is the same in both cases and S is the same in both cases. But what is going to be different is of course the lattice constants A and B will be different. But naturally, if this condition is to be satisfied, the wave which is falling into the crystal, it will be making different angles with respect to the line of atoms along A direction and along B direction, obviously. So that means alpha 0 will be different from beta 0. Beta 0 is the angle that the incident wave S0 is making with the line of atoms along the B direction. So consequently there will be a different angle beta, which we call the scattered angle, with respect to the line along B direction. So only thing is that we will be having another set of equation which is similar, except that S and S0 will be the same in both cases, but the direction cosines will be different, and the lattice constants will obviously be different unless it is cubic, or sorry, in 2 dimension, unless it is square lattice. Okay, so we write it as this LAUE equation is written as a general equation. So essentially what we have is we will be having two sets of equations given by this. They are similar. And what does that mean is that when we started with a single row of atoms, we got for a given S0 for a given alpha 0 direction cosine, we had an angle alpha which indicates a cone, and that cone is in such a way that its half apex angle is alpha, or conical half angle is alpha, and that cone will represent the diffraction condition. So that is the case when we are thinking only about one line of or one row of atoms. So when we add one more row of atoms along the B direction, we have got an extra equation. So that means these two equations should be simultaneously satisfied. That means the diffraction condition is going to be more stringent. So here you can see the illustration. You have got an incident wave coming in this way, which is indicated by S0. So here you have got a two-dimensional lattice, and the primitive translation vectors, in order to identify that, you will have to see what are the directions along which you can see the periodicity. So I will just show you that. So this is one direction along which you can see the periodicity. This is another direction along which you can see the periodicity. So A and B are the lattice constants along those directions, and primitive, if you consider this to be a vector, this vector will also indicate the primitive translation vectors along the first direction, and this is the primitive translation vector along the second direction. Okay, and if you compare it with the previous picture, what you have to understand is that we have got a given incident wave direction, and it is hitting this atom here, and for it can there will be diffraction. You'll have to consider the diffraction condition that is to be satisfied by the row of atoms along this direction and the row of atoms along this direction. So what we have seen from the previous example is that the diffraction condition will be indicated by the diffraction cone. Okay, which means or for a given S0 direction, all the directions or all the waves which are lying on the surface of this cone will be making the same angle with respect to this line, which is the line of atoms along the A direction. So all the waves which are lying on the surface of this cone will indicate the diffraction condition along A direction. Similarly, I got a bigger cone over here that is surrounding the line of atoms along this direction. Okay, and all the waves which are falling on or which are placed along the surface of this bigger cone, it will indicate that they will satisfy diffraction condition by the atoms which are placed along the B direction. So that means actually what we have is we started with a one-dimensional arrangement, but in actual practice, when we actually do the XRD experiment, we just do not have a one-dimensional arrangement alone. The crystals are 3 dimensions, so we have to think about the 3-dimensional periodicity which is appearing in the crystal. So that is why we started with the row of atom, and then we added one more row of atom in the other direction, or we started with the one-dimensional lattice, and then we here what we can see is a 2-dimensional lattice. So in the case of 2-dimensional lattice, we have got 2 cones for a given S0 direction. We have got 2 cones which will be set which are representing the corresponding equations for the diffraction conditions, which means these 2 equations which I mentioned earlier in terms of alpha 0 and beta 0, those 2 equations should be simultaneously satisfied. So one set of those equations will be represented by one of this cone. The second set of equation will be represented by the other cone. So these 2 should be simultaneously satisfied, means the diffraction condition will be met only when only along those directions which are indicated by the intersection of these 2 cones. So that is the interesting thing. So that intersection, so if those 2 cones, if we are projecting it into a 2-dimensional plane, this is how we are going to see. This indicates and it is another interesting way in which we can look at the how those 2 equations are simultaneously satisfied. For example, you can see if you remember those 2 equations, you have got 2 integers E and F. E1 and 2, they stand for different orders of diffraction. When the rays undergo diffraction along diffraction at the atoms which are periodically arranged along the A direction. So that means the cones which represent those diffraction conditions, you can see these are actually part of those cones, and those cones will encircle or they will surround the line of atoms indicated by A bar. Okay, similarly I got other cones and other cones representing different orders of diffraction from atoms which are placed along the B direction. So what since those 2 equations should be simultaneously satisfied, it means intersection of all these cones, these you can see these dots at the intersection. So when these 2 equations are simultaneously satisfied, it means there are a certain specific direction along which only these 2 equations can be simultaneously satisfied, and they are indicated by these black dots here. Now obviously when we extend that to 3 dimensions, we will be having one more set of atoms which are arranged along the C direction, and their direction cosines will also be different, which are given by gamma and gamma 0, and we will use different integer g to represent that equation. So essentially what we have is in order to have diffraction condition to be satisfied from an actual crystal which will be having 3-dimensional periodicity, we'll be having 3 sets of equations which are to be simultaneously satisfied. So that means the diffraction condition is very stringent. It is not easy to satisfy all these equations simultaneously, because on the right hand side you can see the s minus s0, s minus s0, those waves are the same, which means a given incident wave direction S0 and a given diffracted wave direction S. If you actually do the XRD experiment, and if you set a particular angle of incidence, and if you expect to have a bright diffracted spot along a specific direction, it is not so easy to satisfy, or you can say that only for certain diffraction angles this will be satisfied. All these equations should be simultaneously satisfied in order to actually observe a bright diffracted spot in the pattern after diffraction. So these equations together, they are referred to as LAUE equations. Now we will see the equivalence between Bragg equation and LAUE equation. For that we will begin with a simple cubic arrangement. So you have to remember the relation connecting interplanar spacing D, lattice constant A. Obviously, since it is cubic, A, B, C, all these are equal, and H, K and L, they are Miller indices, and in a cubic system this is a relation D is equal to A divided by root of H square plus K square plus L square. What we do is we will just look at the Bragg condition, or the picture that we use for deriving Bragg condition. We will assume a specific case. First specific case is that we are considering a cubic lattice, and then we assume another specific case which is as given in Bragg condition, which means the angle between the incident wave direction, this is the incident wave direction, and the angle between the diffracted wave direction, which is this one, that in this case it is equal to 2 theta. So we consider that specific case where we consider a cubic lattice and the angle between the incident and diffracted beam be 2 theta. Now what we do is we will look at these are the LAUE equations. What we have to do is we square and add the left hand side and right hand side of the LAUE equations. We rearrange them and we will get sine square theta. Okay, and for that we make use of these equations, which is actually the it is the law of direction cosines in solid geometry. We have got these equations. So making use of these two equations, from LAUE equations we will arrive at sine square theta by squaring and adding left hand side and right hand side of equation number 4. Making use of these two equations stand for the law for direction cosines in solid geometry. And similarly we will take Bragg equation, which is n lambda equal to 2d sin theta. From that also we will obtain sine square theta, but since it is cubic lattice we impose this condition also. So essentially what we are going to get is we will get two equations for sine square theta as given here. From LAUE equation you will get this one, and from Bragg equation you will get this for the cubic system. Okay, and if you compare these two equations, you can easily see we have got lambda square by 4a square on both in both equations. So you'll be able quickly we will be able to see that these integers which we used to represent LAUE equations, which are E, F and G, they are related to the Miller indices H, K and L in the Bragg picture, which means E is equal to n H, F is equal to n K, and G is equal to NL. Okay, so that means so how do we say that these two equations are equivalent? When you get this result, it means these two equations are equivalent. But one more point can be added to this. So since we obtain that E is equal to NH, F is equal to NK, and G is equal to NL, E, F and G are the integers which we used for representing the LAUE condition along the A direction, along A direction of atoms, B direction of atoms, and C direction of atoms, let us say. So that means the diffracted beams defined by the integers E, F and G in the LAUE method, they can be taken to be the nth order diffraction from a set of HKL planes in the Bragg treatment. And this when you look at this equation, you can see that this n, which is the order of diffraction in the order of diffraction in the Bragg picture, let us say, that is n will be when you look at this equation, you can see that n will be the largest common factor of the numbers E, F and G. Okay, so that is how we say that these two equations, LAUE equations and Bragg equations, they are actually two different ways in which you can represent the diffraction conditions, but the Bragg condition we can obtain it from LAUE equations, or they are actually they are actually connected, okay, or we can say they are equivalent. Okay.